Good afternoon, guys. My topic for this afternoon will be the derivation of the formula for taking the volume of a right circular cone using vertical slice. The last time around, we discussed the horizontal slice. So this afternoon, I will present the solution using vertical slice. Okay, let's proceed. Lesson number 66, Integral Calculus, Volume, Circular Disc Method. The problem will still be the same like yesterday. It's the derivation of the formula for taking the volume of a right circular cone. But for this afternoon, it is by using vertical slice. So I will read the problem. Using integration, derive the volume of the right circular cone using vertical slice. Vertical slice is something like this. Yesterday, I presented the horizontal slice. Okay. XR minus XL times dy. We rotate this one along the y-axis, but this afternoon we will try to bring out a solution by rotating that vertical slice with respect to the x-axis, so it's vertical. To bring out the figure of the right circular cone on the Cartesian coordinate system, y-axis, x-axis, we could not maintain the upright configuration of the cone, because if we maintain the upright, then we try to rotate it along the x-axis, that will not be possible. So for it to be possible, we lie down the cone, meaning the altitude, the height, should be lying on the x-axis. Okay, so we bring down the cone. So this is actually the base of the cone. This is the tip of the cone. Okay, this is the radius r. This is h. H, it seems it's 0, but it's along the horizontal line. There's nothing wrong with it. Okay. The variable radius is actually y higher, dy here minus dy here, because as the differential slice moves from 0 to h, it varies. Okay, it should be from maximum y higher minus y lower to till 0. Actually, as differential x moves, it varies in height. Okay, it's not a constant thing. So if we try to bring out the one slice and we try to rotate it along the x-axis, it is something like this. Okay, this is the radius r, this is the thickness. Radius r is actually y higher minus y lower. It's still the same procedure, but we are now working on dx. Yesterday it was dy. Okay, let's try to bring out two right triangles. Okay, I bring out this one, it is this, and I bring out the bigger one, it is this. So this is actually the altitude of the cone. This is the radius r. This point here is actually with coordinates xy. Okay. So if the coordinate of this point is xy, this should be x, and this should be y. Okay. This one will be r minus y. So this is r minus y. So by using the smaller right triangle, I call this angle now. Yesterday put the angle to be theta. Let's place it as alpha for the meantime. Alpha. Horizontal line, this is the same straight line. So if this is alpha, this should be alpha. Okay? Let's bring out the solution. Differential volume is differential area times thickness. This volume here, the volume of this one here, should be the area of the circle times the thickness. Differential area times thickness. And the area of the circle is pi times the variable radius quantity square, y higher minus y lower quantity square. Thickness is dx. It is along the x-axis, that's why we call it vertical slice. Okay, equation number 1. Let's now try to bring out the relation of h, r, x, and y. We take the tangent of the first smaller right triangle. The tangent of this angle is opposite over adjacent. So this is r minus y over x. And considering the bigger right triangle, the tangent of this angle will be this side here, all over this. So this is actually r over h. Simplifying this, xr cross multiply equal to h times quantity r minus y. What's this? Hy now will be rh minus hr. We place this on the left, we push it on the right, so this will now be negative. Then we multiply all terms by, we are computing y for y times 1 over h. Okay, so the left hand side, it will now just be simply y, right? And the right hand side, okay, it will be, I factor out, I factor out r, so this is r, times 1 over h, this is over h, times the quantity h minus x. I just bring out the common factor r, okay? That is equation number 2. And what's the significance of this equation number 2? Actually, equation number 2 is y higher. A slanted straight line. It is the equation of this line here. It's a variable line because as it moves from 0 to h, you know, the values are changing. And y lower is a horizontal line. Y lower is equal to 0. This is a horizontal line. Because actually, to get the volume for one complete revolution, okay, the x here is moving like this till it reaches h. So as you notice it, y lower is a horizontal line and the equation of that one is y lower is equal to 0. That's analytic geometry. Okay, getting 1 and 2, back to equation number 1, therefore differential volume will be pi times the quantity. Y higher is r over h times quantity h minus x, minus 0, all quantity square, times dx. Okay, differential volume will be pi r square over h square times the quantity h minus x quantity square times dx. This is now a differential equation. Why differential equation? Because we got differential volume and we got differential x. It is a differential equation. So to find the relation of volume as a function of x, okay, we try to integrate. Right? Lower limit will be 0, upper limit will be h. Okay? These are abscissas. We are using vertical slice. And this dx here moves from 0 to h. So the lower limit is actually 0 and the upper limit is h to complete the taking of the volume for one complete revolution. Okay? This dx here should move from 0 to h. Okay, then we try to rotate it one complete revolution. Okay? The integral of differential volume equal to pi r square over h square, the integral from 0 to h of x minus x quantity square times dx. This now falls under the power formula, where the value of u is the term inside. U is actually h minus x. Du will be equal to, h is constant, so the differential will be 0 minus dx, or du is equal to minus dx. It is not exact. For it to be exact, we introduce negative 1 outside, then we place a negative sign inside, then we can now use the power formula. Therefore, volume now will be negative pi r square. This is a negative 1 times this is negative pi r square over h square times h minus x to the third power over 3 with the limit from 0 to h. Power formula. 2 plus 1 is 3. This is all over 3. So substituting the lower higher limit, if x is h minus h will be 0, 0 cube will still be 0, and 0 over 3 will be 0. So when the upper limit is substituted, the value of the upper limit is 0. Okay? When we substitute the lower limit, the operation is negative, subtraction, right? This is minus. When h is 0, h minus 0 will be equal to h. Therefore, h cube will be equal to h cube. So this is h cube. But this is preceded by negative sign because we are subtracting the value of the upper limit minus the value of the lower limit when they are substituted. I bring out 3 already. So what will come out? This negative, it will now be plus, right? There is no such thing as negative volume. Pi r square over 3h square. H cube can be written as h times h square. So this h square cancel with this. So the final formula for taking the volume will be 1/3 pi r square h. Pi r square h. This is all over 3. Same as yesterday. So the significance of this, even by using vertical slice, the volume derived is still the same. Okay? So whenever you are given a problem and that it does not specify what type of slice you will be using, it's up to you guys. But it's still, the volume will still be equal to 1/3 pi r square. That's the importance of integral calculus, guys. So our topic for this afternoon is actually the derivation of the formula for taking the volume of a right circular cone using vertical slice. That's one topic. Good afternoon, Los Angeles.